Hi, chemistry students. This is your Unit 9 lesson recap on classifications of reactions. This was given live in class, but if you are watching this for review or because you are absent, please be sure that you have your guided notes. In addition, while in class we played the videos that are embedded in this lesson. I will not be doing that for this recap. If you would like to see the videos embedded in this lesson, you will need to go to the slides directly, and you can watch them through the slides that are in the assignment on Canvas. With that, let's get started. So the first type of reaction that you might need to classify is something called a combustion reaction. It is a reaction between a hydrocarbon reacting with oxygen. Now, a hydrocarbon would just be any substance that has carbon and hydrogen in some ratio, and that's what the X and the Y is in terms of the subscripts. Now, there is complete and incomplete combustion. So in complete combustion, the hydrocarbon reacts with oxygen gas cleanly. There's plenty of oxygen around. Recall that oxygen is a diatomic element, so oxygen gas is always O2. When there's abundant oxygen around to react completely with the hydrocarbon, you're given as a product carbon dioxide gas and water vapor. If it's incomplete combustion, that means that there's not quite enough oxygen around to efficiently react with the hydrocarbon. And so you get a variety of products that are a lot dirtier. Things like soot, carbon, or CO, which is carbon monoxide, which is a highly toxic gas, or H2O. Again, as I said, incomplete combustion occurs when there's really not enough oxygen, or the oxygen is not reacting efficiently with the fuel or the hydrocarbon. Incomplete combustion tends to be very smoky and sooty. Here are two examples of balanced reactions using hydrocarbons. Here is methane gas reacting with oxygen to give you soot and water vapor. That black stuff that gets on things called soot. Here's another one where maybe you have a little bit more oxygen and you have some reaction to form carbon monoxide, but not carbon dioxide gas, and water vapor. In both circumstances, if you look at the balance, the reactions are balanced. So we have 2 carbons on both sides, we have 8 hydrogens on both sides, and we have 6 oxygens on both sides of the balanced reactions. Now, complete combustion is clean, and it's what you'll see in a lot of various things, like in propane torches that you might use for heating or burning things. Propane has the formula C3H8. Again, you can see it's a hydrocarbon. It reacts with oxygen to form carbon dioxide and water. Now, in any of these reactions as we're going through, we always start with the skeleton, and that would be the correctly written formulas for both the reactants and the products. Once we have the correct skeleton, we put these lines in front. We have the right formulas, the right packaging. We don't change subscripts. We just add coefficients in sort of a puzzle way in order to make a balance between the atoms and type of atoms that are the reactants versus the products. So with hydrocarbons, generally, since oxygen is in 2 places in the products, we balance the carbon and the hydrogen first, and then fill in the oxygen. So here's the balanced reaction. As you can see, we had 3 carbons, so we put a 3 as a coefficient here, giving us 3 carbons. We had 8 hydrogens, so we put a 4 here, giving us 8 hydrogens here. Then we just need to go back and see how many oxygens we had on this side. Well, we had 6, and 4 is 10, and that's where the 5 here, 10, is balanced. So with hydrocarbons, you always start with the carbon and the hydrogen because they're only in one place. You balance them, and then you go back and you balance the oxygens. So complete combustion is the efficient burning of a hydrocarbon with oxygen gas, which is diatomic oxygen, to form carbon dioxide and water. If you watch the embedded video, you'll get to see this particular young man trying out his new propane torch to a very famous Johnny Cash song. All right, the next type of reaction you're going to have to be able to identify and then predict products is a synthesis reaction. In some textbooks, it's called a combination reaction. It is in our case, we're going to be looking at two elements or compounds to form a single compound, a single entity. We're going to only predict products for very simple synthesis reactions, but you do need to be able to identify them by looking and seeing, well, you've got two things to start and just one thing to begin. Synthesis means combining two things. You can see in our picture, we've got a very hungry bird and a worm, two different entities, and they combine to form this very satisfied fat bird. So here is the synthesis of salt, sodium chloride. The word equation would be sodium metal and chlorine gas combined to form solid sodium chloride. Again, we have a skeleton here. Here's sodium metal, it's a solid, and chlorine gas we recognize as being one of the diatomic elements. So it's Cl2, that's an L, Cl for chlorine, 2, diatomic gas. And we write the correct formula for sodium chloride. We don't write NaCl2 because that would not be balanced in terms of charges. Once we have all the correct formulas written, then we go back and put these lines in to balance with coefficients. If we do that, you will see that since we have two chlorines on this side, we'd have to have put a 2 as the coefficient here, necessitating a 2 here. So we have 2 sodiums and 2 chlorines on the balanced reactant side. And since we have 2 units of NaCl, we have 2 sodium and 2 chlorine on the balanced product side. If you want to see the actual synthesis, you'll go into the slides that are posted on the Canvas site and you can watch this video. All right, the next type of reaction we're going to need to be able to identify is decomposition. You might think of decomposition as something breaking apart. So you can recognize a decomposition because there's generally a single compound. It couldn't just be an element because elements are the simplest form of matter. You're going to have a compound that breaks apart into two things. It might be two elements or it might be two compounds. We're only going to have you predict the very simplest kind of decomposition if we're asking to predict products, but you are going to have to be able to identify them. So what you see here is that in this decomposition of this egg, we have just one thing, one entity as the reactant. It breaks apart into two. So I bet you're surprised. Maybe you thought it would just be a bird coming out of this egg, but turtles also hatch from eggs. So here is a very classic decomposition, the decomposition of water. Water decomposes to oxygen and hydrogen gas. So again, you need to write the correct formula for the skeleton. And the skeleton, the formula for water is H2O. You need to remember that hydrogen gas and oxygen gas are both diatomics, so their correct formula would be H2 and O2. We then add the lines in the front for the coefficients. That's our skeleton that is not balanced but has the correct formulas. And then we're going to need to balance it. Just so you know, to decompose water, you can't just boil it. Boiling water is water vapor. But if you want actually oxygen and hydrogen, you have to have a run electric current through it, and in that case you'll be getting oxygen gas and hydrogen gas in a ratio of 2 to 1. To balance it, you can see we just have one oxygen on this side but 2 on this side, so that's why there was a 2 in front of here. Then we're going to have to balance the hydrogen to get 4 hydrogen. So that would be the balanced equation for the decomposition of water. And if you watch the Google slides and look at the embedded video, you'll actually see that decomposition of water. All right, the next slide shows you the next one you need to remember. It's a double replacement reaction. And sometimes it's called a double displacement reaction. This always happens in solution. You have two ionic compounds that are dissolved in the solution, and they are soluble, which means individually those ionic compounds will dissolve and dissociate in the water. But when they get together, it's almost like going to a party. They switch partners. So you can see here, here's one ionic substance, the penguin with the hat. Here's another ionic substance, the pig with the glasses, and once they get together, they're put together in the water, they switch partners. And again, the cation would have to switch with the cation, or the anion would have to switch with the anion. And so you can see they switch the glasses and the hat. They like the other, and one of these two will be a ionic substance that is insoluble, that precipitates out of the solution. And we'll talk more about that as we go through. But the pattern is that you have two compounds. And you can see, we usually say like inner and outer. So this would be, as you write an ionic compound, you know the cation and goes first, the anion goes second, the cation goes first, the anion goes second. So the A goes with this. The cation goes with the Y, which is the anion of the other, to give you AY. And then the cation of the second goes with the anion of the first to give you CX. Remember, we always write it in order of cation, anion. So you can recognize a double replacement because two compounds become two compounds. Now, what makes this a reaction is the two compounds in the reactants dissolve in the water. So, and then when you put them together, one of the two combinations forms what's called an insoluble precipitate. It's a precipitate that will not dissolve, and you'll actually see it sort of come out of the solution. The solution will get cloudy. Precipitate is a solid. One of the compounds, though, will stay in the solution. So let's look at an example. Predicting products for double replacement reactions. Here are the steps, and this is the main predicting products we're going to be doing in this unit. Magnesium chloride reacts with lithium hydroxide. The first thing you want to do is switch partners before you even write the skeleton and write what the products will be. So magnesium chloride and lithium hydroxide, you're going to go inner outer. Magnesium react with hydroxide. Lithium will react with chloride. So you'll get as your products magnesium hydroxide and lithium chloride. Now it's your job to remember how to write the formulas for 4 different ionic substances. And you have to do that first. Don't try to balance it. Just write the formula for magnesium chloride, then write the formula for lithium hydroxide. Put an arrow, write the formula for magnesium hydroxide plus the formula for lithium chloride. Put lines in front, and then you will balance it later. So if you are doing it correctly, magnesium chloride, which is a 2 plus and a 1 minus, would be MgCl2. Lithium hydroxide will be LiOH. And magnesium hydroxide, though, since lithium's a 1 plus and magnesium's a 2 plus, it'll combine magnesium hydroxide, it'll be MgOH2, and lithium chloride will LiCl. Notice we have not thought about balancing. We have just wrote the formulas for 4 separate ionic compounds. Now we need to balance. That's where these lines come in. And this is, again, we've been practicing balancing, so I'm going to leave it to you to kind of work this out when I show you the balanced equation, but you have to balance. And again, with polyatomics, it's easier to balance them as a unit. So notice what you have to do. You have to add a 2 in front of lithium hydroxide and a 2 in front of lithium chloride to get this to balance. Got 1 magnesium, 2 chlorines, and since this coefficient is here, that makes this 2 chlorines. We have 2 hydroxides here, so 2 in front of this gives us 2 hydroxides, 2 OHs, and 2 lithiums, and 2 lithiums. You'll notice I've put an S next to the magnesium hydroxide because magnesium hydroxide, when it forms, will not dissolve in water. It'll come out as a solid. Lithium chloride, on the other hand, will stay dissolved, and that's why it still says aqueous. Let's try one more. So this is the reaction. I want you to sort of look at this picture. Here we had the 2 solutions. When we combine them, you get this yellow cloudy precipitate. So this is lead 2 nitrate. That's what's in the upper container. Initially, you had sodium iodide in the lower container. You can see when they're combined, something comes out. So again, we're going to do inner outer. So the product would be lead 2 iodide and sodium nitrate. Now we have to write the correct formulas before we even think about balancing. So here are the correct formulas. For lead 2 nitrate, for sodium iodide, again, using the charges. Sorry, there's an extra AQ down here, but that's aqueous. They always are both soluble to begin with. But then when we make the other combinations of lithium 2 iodide and sodium nitrate, only one of them comes out of a solution, and that's going to be the lead iodide. That yellow there is lead iodide, and I guess this aqueous needed to be with the sodium nitrate. It stays in solution. Now we need to balance this equation. We have written the correct formulas. That is an absolutely essential step. You cannot start balancing with subscripts. Don't do it. It's the packaging. Write the correct formulas first and then go back and balance. Here's the balanced equation. You can see that we have one lead on this side, one lead on this side. We have 2 nitrates and 2 nitrates. We have 2 sodiums and 2 sodiums, and we have 2 iodides or I's and 2 I's here. We add coefficients to balance. Once we have the correct formulas, we do not change them. You'll get lots of practice on this. Okay, and if you watch the video embedded, you will see this reaction in action. Okay, now there is one special type of double replacement where the product is not a precipitate, where it's just water. And this is called a neutralization. You've probably heard of that. It's an acid plus a base to give water an ionic compound. And you can recognize an acid because instead of having a metal here, you will have hydrogen as the ion, and the base is always a metal and hydroxide. So outer is HOH, which is just water. So instead of having a solid precipitate, you form water, and then the second thing will be an ionic compound like sodium chloride. We will talk much more about this type of double replacement during our unit on acids and bases, but you should be able to recognize it. All right, final type that we're going to talk about is something called a single replacement reaction. In a single replacement reaction, a more active element replaces a less active element. So let me show you this analogy. And this is kind of a sad story of some people I knew in high school. Or a story, I don't know if it's sad, probably worked out okay. But Joe and Sally were a couple all through high school. A compound. They were bonded to each other quite closely all through high school. Joe here represents the cation in this particular analogy, and Sally the anion. Now here we had Todd come in later on in our high school career, and Todd was a much more active young man. He worked out more. You can see he's more muscular than Joe here, and unfortunately, Sally was not particularly interested in brains. She was more interested in brawn. And so the more active Todd replaced her boyfriend, Joe, who got kicked out. And a new compound, a new bond was formed here. Now, that's not to say in a different circumstance you couldn't kick out somebody else, but I'm just saying in this circumstance, if Todd and Joe are representing the metal and the metal cation, the metal has to replace the metal cation in this particular circumstance. And Sally represents the non-metal anion. But again, in a single replacement reaction, it can only happen one way, where a more active metal replaces a less active metal. So let's see if I can sort of show you this in terms of chemical terms. Now, how do you tell who's Todd and who's Joe, who's more active? Well, we have a ranking system, and it's found experimentally called the reactivity or the activity series of metals. And it essentially says who is the most active, got the biggest muscles, and who has the least biggest muscles. So anybody on top can replace anyone on the bottom in a compound. Everybody wants to be in the compound because in that regard, they will be an ion that looks like a noble gas. So potassium can replace sodium, potassium can replace calcium, potassium can replace magnesium in a compound, but it will not happen in reverse. Magnesium cannot replace potassium, calcium cannot replace potassium. Again, we're going to get some practice with this. Let me show you. So again, the pattern for a single replacement is a compounded element giving you another compound and another element. So the cation will replace the cation, or the anion will replace the anion. And you will always have to check the activity series to see if the reaction would actually happen. We're going to look at one that actually happens. Here's the words. Copper, which is a more active element, and silver nitrate react to form copper-2 nitrate and silver. We may be demoing this in class, but you can see the picture here. Here is copper, solid copper, this copper wire, and it's immersed in a solution of silver nitrate. What happens is that the copper replaces the silver in the aqueous solution, and the silver gets kicked out. You'll notice that right on the surface of the copper, you have this silver precipitate forming. So the silver is actually forming on the surface of the copper. You can see the solution turns blue because copper ion, when it forms a blue ion. So how do we balance it? Well, here is our skeleton. We have copper solid, the wire, reacting with silver nitrate. And again, AgNO3 is silver nitrate. To form copper-2 nitrate, so here's the correct formula for copper-2 nitrate, and silver metal. That's why it's solid. So you have an element and a compound reacting with another, reacting to form another compound and an element. And again, if you check the activity series, you'll see that this does occur. We'll balance it again with coefficients once we've written the correct formulas. And again, as you can see, copper can replace silver. So just going back, notice copper can replace silver. Now, if we had put silver in copper nitrate, that would not occur because silver is not tough enough to replace copper in a reaction. Now, nonmetals can also replace nonmetals. So here's another one. Aluminum iodide reacts with bromine to form, and aluminum bromide and iodine. Here is the skeleton. Here's aluminum. Again, you have to make sure that you're balancing based on charges. You have to remember that the halogens, like bromine, are diatomic. Once you've written the correct skeleton, you will balance using coefficients, and there you go. And again, the basic procedure is to identify the pattern and the type for predicting products. You write or say the products in words. You write the skeleton, being sure to have the correct formula for each element, and then you balance with coefficients. And again, here are the patterns that you're going to need to remember. Be sure you always are consulting your notes and practicing this. And Dancing Jelly Man is very glad that this is over.